Welcome back to the Deep Dive. Today, we are wading into what is, I think, arguably one of the most complex and honestly terrifying subjects in all of human biology. We're talking about neoplasia.
It really is the emperor of all maladies, isn't it? It's just a massive, massive topic.
It is, and I think to really get our heads around it, we have to start by taking apart a really common misconception.
Okay.
I think for most people, when you hear the word cancer or tumor, you just imagine biological anarchy.
Right. Total chaos.
Exactly.
Yeah.
Like the body has just lost its mind, cells are going haywire, everything is breaking down, total disorder.
That's the popular idea, for sure. The idea of, entropy just taking over the system.
But looking at the two sources we're diving into today, and we are really drawing from the absolute heavyweights here, Robbins and Cawthron, pathologic basis of disease, and Underwood's pathology, the picture they paint is...
Well, it's actually quite different. It isn't really chaos, is it? No, not at all. And that is the central tension, I think, that you have to hold in your head for this entire deep dive. Cancer isn't cellular chaos. It is a disease of altered rules.
Altered rules. I like that.
It's not that the cells have forgotten how to function. It's that they have acquired new priorities.
A new mission statement.
Exactly. It's a highly structured, almost logical evolutionary process where the rules of cooperation, the social contract of the body, if you want to call it that, they're replaced by the rules of survival, replication, and persistence. The cancer cell is actually hyperfunctional.
In its own context.
In its own terrible context, yes. It's just working for itself now, not for the whole organism.
So our mission today is to try and synthesize these two incredible texts. We're using Robbins for that big picture, that unifying systems framework, sort of the how it all fits together.
The breadth.
And then Underwood comes in with that sharp mechanistic clarity, viewing the disease specifically as a response to injury.
Correct. And I have to say this right at the top, because we are going deep today. What we're doing here is building a conceptual map.
Right.
We're sketching the terrain. This deep dive, it's a revision scaffold. It is absolutely not a substitute for the textbooks.
Absolutely not.
You still have to go read the chapters. I mean, we can give you the keys, but you have to get in and drive the car.
Yes. Consider this the trailer for the movie,
right,
but you've got to go see the film. So with that said, let's start at the very, very beginning. The word itself, neoplasia.
Literally, it's from the Greek. It just means new growth.
Simple enough. But new growth is, well, it's vague. A wart is a new growth. A callus you get from lifting weights is a new growth. And a glioblastoma is a new growth. We need a more precise definition to separate, the killer from the mere annoyance.
We do. And Robbins gives us what is really the gold standard definition. It defines neoplasia as a disorder of cell growth triggered by mutations affecting a single cell and its clonal progeny. But the key part of that definition, the part that really matters, the bit you need to underline in your mental notes, is that the growth is autonomous.
Autonomous. So it doesn't listen to anyone else. It's gone rogue.
It means it persists after the initiating stimulus is removed. And this is the crucial difference between neoplasia and things like, say, hyperplasia or hypertrophy.
Okay, so let's use the weightlifting example.
Right.
I get a callus on my hand or my biceps get bigger. That's hyperplasia and hypertrophy.
Right. And why is it there?
Because of the stress of the weight.
Yeah.
It's a reaction.
Exactly. It's reactive. Now, what happens if you stop lifting weights for 6 months?
The callus softens up, the muscle shrinks. It's a sad but true story.
Right. The stimulus is gone, so the growth stops and it reverses. The body says, okay, we don't need this extra tissue anymore. But with a neoplasm...
Doesn't care.
It couldn't care less. With a neoplasm, the genetic alterations have been hardwired. They've been passed down. The on switch is jammed. Even if you remove the carcinogen that started it, let's say you stop smoking today, the lung tumor that's already formed doesn't shrink.
It keeps going.
It continues to grow. It has declared independence from the body's regulatory systems. It is, for all intents and purposes, an autonomous entity.
That is, in a way, terrifyingly impressive. It's like a machine that just generates its own power.
It is.
Now, before we get into the mechanics of that machine, we should probably clear up some of the terminology. We use tumor and cancer pretty interchangeably in just, casual conversation.
Everyone does.
But the texts make a really sharp distinction.
They do. A tumor is actually an ancient term. Originally, it just meant swelling.
Oh, really?
Yes, it was one of the cardinal signs of inflammation. Rubor for redness, dolor for pain, calor for heat, and tumor for swelling.
So you could have a tumor just from twisting your ankle.
You absolutely could. But over centuries of medical history, its meaning narrowed, and it became equated specifically with a neoplasm.
I see. Okay, so what about cancer?
Cancer has a much more evocative, almost poetic origin. It comes from the Latin word for crab.
A crab.
Yes.
Because it pinches.
Because of the way it adheres so obstinately to tissues,
Well,
if you actually look at an invasive tumor, particularly something like a breast carcinoma, it doesn't just sit there like a smooth ball.
it's not contained.
No, it has these extensions, these legs reaching out into the surrounding tissue, grabbing hold.
Like the legs of a crab digging into the sand.
Exactly that. It grabs hold and it will not let go. That visual of the crab clinging to the flesh is what gave us the name.
Wow. That's a visceral image.
Mm.
So whether it's a crab-like cancer or a benign lump,
Right?
Robbins breaks down the structure of all these things into two main parts.
Yes.
The parenchyma and the stroma.
Uh-uh.
This is a dichotomy that I see coming up constantly in
Yeah.
pathology.
It's absolutely fundamental. You have to get this. Think of a tumor like an organization. The parenchyma is the functional part. These are the neoplastic cells themselves.
The workers.
The workers, or maybe the mobsters running the operation, they're the ones that determine the behavior of the tumor, and they determine its name. If it's a colon cancer, the parenchyma are the mutated colon cells.
Okay,
Yeah.
simple enough. And the stroma.
The stroma is the infrastructure. It's the office building they work in. It's the connective tissue, the blood vessels, the immune cells, the scaffolding that holds it all together.
And the tumor needs both. It can't be one without the other.
It absolutely needs both. The parenchyma might be the bad guys, but they can't survive without the stroma, the roads, the water pipes, the electricity feeding them and supporting them.
Yeah.
You can't just have a tumor of floating cancer cells. They need a bed to lie in.
And there's this specific interaction here that I found really fascinating in the reading. Desmoplasia.
Yes,
It sounds a bit like a heavy metal band, doesn't it?
it does. We are desmoplasia, and it's actually quite metal in its nature. It refers to when the parenchymal cells, the cancer cells, actively stimulate the stroma around them to form this abundant, dense collagen.
They're building a wall.
They're forcing the stroma to build a fortress around them. It's a scar-like reaction.
And this changes how the tumor physically feels, right?
Drastically. It makes the tumor stony hard. This is the origin of the term serous tumor.
Yeah.
If a surgeon feels a breast lump and it feels like a hard rock or a marble in the soft tissue,
That's desmoplasia.
that's the desmoplastic reaction. That hardness isn't actually the cancer cells themselves. It's the scar-like stroma that they have tricked the body into building for them.
So the body is essentially being co-opted into protecting its own killer.
Precisely. It's a recurring theme.
Wow. Okay, so we've got the definitions down. We know the parts. Now we face what you said is the most critical question in all of pathology. The great divide. Benign versus malignant.
This is it. This is the single most important decision a pathologist makes every single day. A patient's life, their treatment, their prognosis. It all hangs on this distinction. And the tricky part is it's not always obvious to the naked eye.
Right. We tend to think pretty simplistically. Benign is good, malignant is bad.
Mm-hmm.
And, I mean, generally that holds up, doesn't it?
Generally, yes. A benign tumor is localized. It's usually amenable to surgical removal. It hasn't spread. You cut it out. The patient usually survives. It's fundamentally a mechanical problem.
Robbins points out this really critical exception where benign isn't necessarily good. It all comes down to location, location, location.
Exactly. You can have a biologically benign tumor, meaning it's not spreading, it's not invading. But if that tumor is growing inside your skull and pressing on your brainstem,
It's lethal.
it's lethal. It's a benign tumor with a malignant clinical outcome. So we always have to separate the biological behavior from the clinical consequence.
That's a great point. But when we use the word malignant on a pathology report, we're implying something very specific about its behavior, regardless of where it is.
Yes. Malignant means it is invasive and it is metastatic, or at least has the potential to be. It means it is capable of killing by spreading and destroying tissue. It has no respect for boundaries.
So when a pathologist gets that slide, they've got the pink and purple stain,
Yeah.
the H&E. They were looking for specific clues to tell them, is this the crab or is this just a well-behaved lump?
Mm-hmm.
This brings us to two massive concepts, differentiation and anaplasia. I like to think of this as the face of the tumor.
That's a good way to put it. Differentiation asks a simple question. How much does this tumor cell look and act like the normal cell it came from? How grown up is it? How much does it resemble its parent tissue?
So if I have a lipoma
Mm.
A benign fat tumor. It looks like fat.
Exactly. A lipoma is what we call well-differentiated. Under the microscope, it looks almost exactly like normal adipose tissue. A novice might not even realize it's a tumor until they zoom out and see that it's forming a discrete mass.
So it still remembers who it
It
is.
remembers its heritage. And benign tumors are almost always well-differentiated.
How about malignant tumors?
Yeah.
They start to forget. They have amnesia.
They have a range. Some malignant tumors are well-differentiated, but many are poorly differentiated. And at the extreme end of that spectrum, when they lose that resemblance entirely, when they look like absolutely nothing recognizable, when they just look like primitive, chaotic blobs.
That's anaplasia.
That's anaplasia. It literally means backward formation. It's a regression to a more primitive, undifferentiated state.
So let's paint that picture. What does anaplasia actually look like? If I'm looking down the microscope, what are the ugly features, as the books call them, that scream cancer?
It's a real horror show at a cellular level. There are specific hallmarks you look for. First, you have pleomorphism, variation. Normal cells in a tissue are pretty uniform. They look like soldiers in a line, all the same size and shape. Anaplastic cells vary wildly. Some are tiny, some are giant, hulking, multinucleated monsters, all jumbled together.
So visual chaos.
Visual chaos, yes. Then you have hyperchromasia. The nuclei stain incredibly dark blue, almost black.
And why? Why the color change?
Because they're just packed with DNA. They are churning out genetic material, ramping up for division. The nucleus becomes this dense, dark ink blot.
And the size of the nucleus changes too, right? Usually a cell is mostly cytoplasm, the body of the cell, with a small nucleus, like a brain, in the middle.
Right. A normal nuclear to cytoplasmic ratio is maybe 1:4 or 1:6. 1 part nucleus, 4 parts body. In anaplasia, that ratio shifts dramatically, sometimes to 1:1. The nucleus takes over. It's all brain and no body.
And then there's the activity, the actual dividing, the mitosis.
High mitotic activity is a bad sign, sure, but lots of normal tissues divide, like your skin or your gut. What's really concerning in cancer, specifically in anaplasia, is that you see atypical mitosis.
What's an atypical mitosis?
Normal cell division is this neat, choreographed ballet. The chromosomes line up perfectly, they pull apart symmetrically. In anaplastic cells, you see these bizarre, chaotic figures, tripolar spindles, where it looks like the cell is trying to divide into 3, or star-shaped mitosis. It's like a multi-car pileup during the division process.
And finally, Robbins mentions loss of polarity.
This is all about orientation and architecture. Normal tissues have a structure. Epithelial cells know which way is up, the lumen or the surface, and which way is down, the basement membrane.
They respect the line.
They respect the line. Anaplastic cells have zero respect for boundaries or orientation. They grow in disorganized sheets and masses. They are true anarchists at the tissue level.
Okay, so we've identified the ugly features. We know it's malignant. Now we have to give it a name. And medical terminology can feel like a secret code. But Robbins lays out the logic pretty clearly.
It is a code, but once you crack it, it's very consistent for the most part. We break it down by the tissue of origin.
Okay, let's do a quick quiz then. If it's mesenchymal, so connective tissue, bone, muscle, fat, and it's benign, it usually gets the suffix oma.
Correct.
So a benign tumor of fibrous tissue would be
A fibroma.
cartilage,
Chondroma.
bone.
Osteoma. See? Simple.
Easy enough. But if it turns malignant,
Then we have a sarcoma.
Yes.
So a malignant fibrous tumor is a fibrosarcoma. Malignant cartilage is a chondrosarcoma. Malignant bone is an osteosarcoma. Sarcoma implies fleshy. These tend to be these big, fleshy, malignant masses.
got it. Okay, now what about epithelial tissue? The linings of our organs, the skin, the glands. This is where most common cancers come from, right?
By far, over 80%.
So benign epithelial tumors.
They're often called adenomas if they're glandular in origin, like a polyp in your colon. Or they can be called papillomas if they have these finger-like projections, like a wart on your skin.
And the malignant versions, the really bad ones.
They are the carcinomas. That's the big word. So a malignant tumor of gland-forming cells, say in the breast or the colon or the lung, is an adenocarcinoma.
Oh.
And if it looks like the squamous cells of your skin, it's a squamous cell carcinoma.
Okay, that seems pretty consistent. But I know there are traps here. The texts warn us about the confusing ones, the names that sound benign but are absolutely not.
The linguistic traps, yes, you have to be very, very careful here. The big ones are lymphoma, melanoma, seminoma, and mesothelioma.
They all end in oma, which we just said usually means benign.
Right. It's a historical quirk. But these are always malignant. There is no such thing as a benign melanoma. If you see the word melanoma on a report, it is cancer. Full stop. It's just a relic of historical naming that stuck before we formalized the system.
So context is key. Don't just trust the suffix blindly.
Never trust the suffix blindly.
Okay, we've talked about the face of the tumor, the differentiation. But Underwood argues that the single most important criterion for malignancy, right up there with metastasis, is something else.
It's invasion.
Invasion is the defining line. Literally, this is the difference between pushing and breaching.
Explain that. Benign tumors tend to be expansile. They grow like a balloon inflating. They push the normal tissue aside, compressing it. And because they push so slowly and uniformly, they often develop a fibrous capsule around them, a rim of compressed tissue that neatly separates them from the healthy body.
So they stay in their lane.
They stay in their lane. They respect the fence. Malignant tumors do not. They are poorly demarcated. They infiltrate. They send out those crab-like legs we talked about into the surrounding tissue.
Right.
Underwood has this beautiful phrase for it: biology pushed beyond cooperative limits. They don't just push, they breach the boundary.
And that breaching, that infiltration, is what makes them so dangerous to remove surgically.
Precisely. Think about it. With a benign encapsulated tumor, a surgeon can often shell it out. It just pops out like a pea from a pod.
Clean margins.
Clean margins. With a malignant tumor, where is the edge? You can't see it with your naked eye. Those microscopic tentacles of cancer cells might extend centimeters beyond the visible mass. That's why surgeons have to take a wide margin of what looks like healthy tissue just to be sure they got it all.
That makes perfect sense.
Oh.
Okay, so we've set the stage. We know what it looks like, how it's named, and how it behaves at the macro level. But now we really need to look under the hood. What is driving this? We're moving into section 2, the molecular engine.
This is where the revolution in our understanding of cancer has happened in the last few decades. We've gone from just describing the shape of the tumor to really understanding the code that built it. And what we now know, without a shadow of a doubt, is that cancer is fundamentally a genetic disease.
We need to clarify genetic, though. It doesn't necessarily mean hereditary in the way we usually think of it, like passing on blue eyes or your height, right?
That's a great point. It can be hereditary, but usually it's somatic. It starts with a single precursor cell, what we call a monoclonal origin, that acquires non-lethal genetic damage at some point during your life.
And here Robbins makes this crucial distinction between two types of mutations, drivers and passengers. I love this analogy because it explains so much about why cancer is so hard to treat.
It's very intuitive, isn't it? Driver mutations are the ones that actually confer a growth advantage. They're the ones with their hands on the steering wheel, actively driving the car off the cliff. They cause the malignant phenotype.
And the passengers?
Passenger mutations are just along for the ride. They happen because the cancer cell's genome has become unstable and it's making a lot of mistakes. It's like a bad typist. But these typos don't necessarily contribute to the disease. They're just noise in the system.
So if we want to stop the car, we have to target the drivers. Going after a passenger mutation does nothing to slow the car down.
Exactly. And the great challenge of modern cancer genomics is finding those 2 or 3 critical driver mutations amidst the thousands of passenger mutations.
So Robbins categorizes these driver genes into 4 main classes of regulatory genes. I think of them as the controls of the car. Let's walk through them. Class number 1, the gas pedal.
These are the proto-oncogenes. And it's important to say, in a normal cell, these are good genes. They promote normal, controlled growth. They're involved in regeneration and healing, but when they get mutated, they become oncogenes.
They get stuck in the on position, the gas pedal's floored.
Precisely. It's a gain-of-function mutation, and because it's a gain-of-function, you only need one bad copy of the gene to cause trouble. It acts in a genetically dominant fashion. If one of your feet is stomping on the gas, the car is going to go even if the other foot is off the pedal.
So what are some examples of these heavy feet on the gas pedal?
The classic one is RAS. It's a point mutation found in a huge number of pancreatic and colon cancers. It's a signaling molecule that just gets stuck in the active state, constantly telling the cell to grow.
And there are others.
Oh yeah. You have genes like HER2 in breast cancer or MYC in many tumors, which often get amplified, meaning the cell just makes way too many copies of the gene, so you get a massive overdose of the protein.
And MYC is basically the master regulator, right?
MYC is a master transcriptional regulator. It's like a conductor of an orchestra that's only playing pro-growth music. It orchestrates the expression of hundreds of other genes that are all involved in proliferation. When MYC is dysregulated, the cell is just constantly being screamed at, grow, grow, grow.
Okay, so the gas pedal is stuck to the floor, but normally a car has brakes. That's class number 2.
The tumor suppressor genes. These are the brakes. They apply the stop signals to proliferation. They are the guardians of restraint.
And unlike the oncogenes, for these to fail, you usually need to lose both copies, right?
Exactly. This is the basis of Knudson's famous two-hit hypothesis. It's a loss-of-function mutation, which is usually recessive. If you have one good brake, you can usually still stop the car. You need to cut both brake lines to really cause a crash.
And the most famous brake, the one Robbins calls the governor of the cell cycle, is RB.
The retinoblastoma gene. RB sits at a critical checkpoint in the cell cycle, the G1S checkpoint. Think of it as the bouncer at a club. It stands at the door and decides if a cell is ready and worthy to enter the phase of DNA synthesis and division. If the cell is stressed or not ready, RB says no, clamps down, and stops proliferation.
But if RB is mutated and knocked out,
The bouncer is gone, the velvet rope is down, the cell just blows right past the checkpoint and divides when it shouldn't. But there's another suppressor that is arguably even more famous and more important.
TP53.
The one and only, the guardian of the genome.
It's an amazing gene.
TP53 is incredible. It's a sensor. It senses all kinds of cellular stress DNA damage from radiation, chemicals, simple mistakes in replication. If it sees damage, its first job is to pause the cell cycle.
It calls a timeout.
It calls a timeout to allow for repair. It buys the cell time. But it has a second, even more critical function. If the repair mechanisms fail, if the damage is just too great to fix, P53 triggers apoptosis.
Program cell suicide.
Yes. So it's the mechanic and the executioner.
Wow.
It says, fix it or die. And here's the really staggering statistic. Loss of TP53 function is found in more than 50% of all human cancers. It is the single most common genetic abnormality in neoplasia. Without it, cells that have damaged DNA just keep dividing, accumulating more and more mutations. The guardian is dead, and the gates to chaos are wide open.
That gives me chills. So we have the gas pedal stuck, the brakes cut. What's class number 3?
Apoptosis regulators. These are the genes that control that life or death decision. You can think of them as the emergency stop or maybe the zombie factor.
The zombie factor.
Yeah, genes like BCL2. Normally, cells are programmed to die if they're old, damaged, or just not needed. BCL2 is an anti-apoptotic protein. Its job is to keep cells alive. In diseases like follicular lymphoma, BCL2 gets overexpressed due to a translocation.
So the cell becomes a zombie. It just won't die, even when it should.
Essentially, it just accumulates. It doesn't necessarily proliferate faster. It just refuses to leave the party. The room just gets more and more crowded with these immortal cells.
And that leaves class 4, the DNA repair genes.
The mechanics. These are the caretaker genes. If you lose these genes like BRCA1 and BRCA2 in breast and ovarian cancer, or the mismatch repair genes in Lynch syndrome, you develop what we call a mutator phenotype.
Meaning you make more mistakes.
You can't fix your typos, your spell checker is broken, so mutations, both driver and passenger, pile up at an accelerated rate. You are driving a car that is actively falling apart, and you've just fired the entire mechanic crew.
Gas pedal, brakes, emergency stop, and the mechanics. It's a perfect storm of failure.
But Robbins adds this other layer of complexity that I think is crucial for modern understanding. It's not just the DNA sequence itself, it's epigenetics.
Right. This is huge. It turns out you don't actually have to mutate a gene to turn it off. You can just silence it.
How does that work? Methylation is the main mechanism. It's a chemical tag, a methyl group, that gets added to the DNA. Think of it like putting a padlock on the gene. Hypermethylation can shut down a tumor suppressor gene just as effectively as deleting it.
So it's like gluing the pages of the instruction manual together so they can't be read.
That's a perfect analogy. The information is still there, but it's completely inaccessible to the cell's machinery.
Incredible. So when these genetic and epigenetic accidents happen, they give the cancer cell new capabilities, not just growth, but what I think of as superpowers. This brings us to section 3, the hallmarks of cancer. This is the famous framework from Hanahan and Weinberg.
This is really the gold standard for understanding how cells achieve malignant behavior. It's not random. It's a checklist of capabilities that a cell has to acquire. To be a successful cancer, you basically have to collect the whole set.
Let's run through them. We've actually touched on a few of these already. First, self-sufficiency and growth signals.
This is the cell making its own growth factors. It creates what we call an autocrine loop. It's talking to itself, constantly telling itself to grow. Or it tricks its normal neighbors into making growth factors for it.
Next, insensitivity to anti-growth signals.
That's ignoring the brakes. That's ignoring RB and TP53. The do not enter signs on the road mean absolutely nothing to it.
Evasion of apoptosis.
That's surviving stress and damage that should kill them. That's the zombie trait we talked about with BCL2.
Now, here's a big one that we haven't touched on yet. Limitless replicative potential. Because normally, cells have a built-in limit, don't they? The Hayflick limit.
Right. This is the biological clock that's ticking in almost every one of your cells. Normal cells can only divide a certain number of times, maybe 60 to 70 times, and then they stop. They enter a state called senescence.
And why is that? What's the clock?
The clock is at the ends of our chromosomes. They're capped by these protective sequences called telomeres.
I've heard them compared to the plastic tips on shoelaces.
That's exactly what they are, the aglets on shoelaces. Every time the cell divides, the DNA replication machinery can't quite copy the very end, so the telomere gets a little bit shorter.
The plastic phrase, lol.
Plastic phrase. Eventually, the plastic is gone, the chromosome end is exposed, the cell detects this as DNA damage, and it shuts down. It retires.
What cancer cells?
They cheat death. They find a way to reactivate an enzyme called telomerase.
What does it do?
Telomerase is an enzyme that rebuilds the telomeres. It puts new plastic tips on the shoelaces after every division. It is reactivated in 85 to 95% of all human cancers. It essentially makes the cell immortal. It can divide forever.
That is profound. They unlock the fountain of youth, but they use it for destruction. Okay, next hallmark. Sustained angiogenesis.
This is crucial logistics. A tumor cannot grow larger than about 1 to 2 millimeters without a blood supply.
Why that specific size?
It hits a diffusion limit. Oxygen and nutrients can only diffuse so far into a clump of cells. After a millimeter or two, the cells in the center start to starve and suffocate.
So it has to build its own roads to get supplies in.
It has to. It flips what we call the angiogenic switch. It starts pumping out pro-angiogenic factors, the most famous of which is VEGF, vascular endothelial growth factor, to call in new blood vessels from nearby tissues. It's sending out a signal, come here, feed me.
But these aren't normal, well-constructed blood vessels, are they?
Not at all. Robbins describes them as leaky, tortuous, and messy. They're hastily built roads, but they do the job. They bring in oxygen and nutrients, and very importantly, they also provide an escape route for metastasis.
Of course. Okay, what about metabolism? The Warburg effect. This one always seems so counterintuitive to me.
It is. On the surface, normally our cells use oxidative phosphorylation in the mitochondria because it's incredibly efficient. It makes tons of ATP energy from one molecule of glucose.
Right.
Cancer cells, famously, shift to aerobic glycolysis. This is basically fermentation. They do this even when there's plenty of oxygen around, which is the weird part.
But fermentation is so inefficient. It produces way less energy per glucose molecule. Why would a fast-growing cancer cell choose a less efficient energy source?
Because it's a strategic trade-off. They don't just need energy. They need stuff. They need biomass.
Building blocks.
Exactly. They need to replicate their DNA, their membranes, their organelles to make a whole new cell. And it turns out that the intermediate steps of glycolysis provide the carbon backbones, the Lego bricks that are needed to build all of that new stuff. They sacrifice energy efficiency for production of biomass.
That is a brilliant diabolical adaptation. It's not wasting glucose, it's repurposing it for construction.
Precisely.
And finally, the last of the core hallmarks, evasion of immune destruction.
This has been a huge area of progress. We used to think the immune system just somehow missed cancer. Now we know that's not true. Cancer actively and cleverly suppresses the immune system.
How does it do that?
A few ways. They can downregulate MHC molecules on their surface, which is how T cells recognize them. It's like putting on an invisibility cloak. Or, and this is the basis for modern immunotherapy, they express so-called checkpoint proteins, like PD-L1. This protein essentially reaches out and shakes hands with a killer T cell and delivers a signal that says, I'm one of you, nothing to see here, move along. It's a friendly fire-off switch.
Which explains why checkpoint inhibitor drugs like Keytruda and others are such a massive deal now. We're blocking that handshake.
We're unmasking them. We're cutting the brake lines on the immune system's attack so it can finally see and kill the tumor.
So we have this checklist of hallmarks, but a cell doesn't just wake up one day with all of them, right? This has to take time. This leads us right into section 4, evolution and progression.
This is the concept of multi-step carcinogenesis. Cancer is not a single event. It is an accumulation of hits over many years, sometimes decades. You don't acquire all the hallmarks at once.
And Underwood breaks this process down into initiation, promotion, and progression.
Right. Initiation is the first hit. It's an irreversible, permanent DNA damage, a mutation, but, and this is the key part, an initiated cell is not cancer yet.
It's just a loaded gun.
It's a loaded gun sitting there. It might sit there for the rest of your life and do nothing.
It needs a trigger.
It needs promotion. Promoters are agents that stimulate proliferation, but they don't cause mutations themselves. Things like hormones, chronic inflammation, certain chemicals, they force that single initiated cell to divide. And when it divides, the mutation is passed on to its daughter cells. Now you have a small clone of initiated cells.
And then comes progression.
Progression is the slide into true malignancy. This is where Darwinian selection kicks into high gear within the tumor.
Explain that in the context of a tumor. We usually think of Darwin with, finches on an island.
Think of the tumor as the island. It's an ecosystem, and it's not made of one uniform type of cell. As these cells divide rapidly and unstably because they've lost p53, their spell checker is broken, they acquire new random mutations. You get subclones. Some cells are red, some are blue, some are green.
So you have this diverse population of bad guys all living together.
And they are competing. They compete for oxygen, for glucose, for space. The cells that happen to acquire new mutations that allow them to grow faster or resist drugs or survive in low oxygen, they win.
Survival of the fittest.
Survival of the fittest and the most malignant. They outcompete their neighbors, survive, and reproduce.
So by the time we actually diagnose a cancer in a patient, we aren't fighting a single uniform enemy. We're fighting the winner of a ruthless internal evolutionary cage match.
Exactly, which is why chemotherapy resistance is such a massive problem. You treat the patient with a drug and you kill 99.9% of the cells, the susceptible ones. But that 1 in a million cell that had a random mutation allowing it to pump the drug out, it survives.
And now it has the whole island to itself, all the resources.
Right. It grows back, and now the entire tumor is made of that resistant clone we've inadvertently selected for the superbug.
That is it's sobering. It's evolution and fast forward happening inside a person. Now, the most dangerous adaptation of all is the ability to leave home. To travel. Metastasis. Section 5.
This is the metastatic cascade. And Robbins makes a point to emphasize that this is an incredibly arduous and inefficient journey for a cancer cell.
Really? I always assumed they just sort of flake off, float away, and plant somewhere else easily.
Not at all. The bloodstream is an incredibly hostile environment. There's high shear stress from the blood flow. It literally tears them apart. And the immune cells, NK cells, are patrolling like sharks. It only takes a few survivors to kill the patient, but the attrition rate for circulating tumor cells is massive.
So let's walk through the steps of this Mission Impossible. First, they have to get out of the primary tumor. They have to let go.
Invasion. Step 1 is loosening. Normal epithelial cells are glued together tightly by a protein called E-cadherin. It's the cement between the breaks. In many carcinomas, E-cadherin function is lost. The cells detach. They become free agents.
Then they had to get through the floor, the basement membrane.
Degradation. That's step 2. They secrete enzymes, particularly MMP's matrix metalloproteinases. These are enzymes that literally chew through the collagen and proteins of the basement membrane. Think of it as a molecular blowtorch cutting through a steel wall.
And then locomotion.
They literally have to crawl through the hole they just made. They use autocrine motility factors and grab onto the matrix with proteins called integrins to pull themselves forward, hand over hand, through the breach.
So they break out, they crawl to a blood vessel or lymphatic vessel, and they get in. That's dissemination. You said they're vulnerable here. How do they survive?
One very clever strategy is the buddy system. They clump together with platelets.
Platelets, the things that cause blood clots.
The very same. They activate platelets, which then coat the cancer cells, forming a little tumor platelet embolus. This little shield protects them from the sheer stress, and crucially, it helps to hide them from the immune system. It's a disguise, a wolf in sheep's clothing.
That is sneaky. So they survive the journey, and then they have to find a place to land. This is homing.
This is the classic seed and soil hypothesis, which goes back over a century but is still incredibly relevant.
Explain that.
The seed is the tumor cell. The soil is the target organ. Sometimes where it lands is just a matter of anatomy. Colon cancer often goes to the liver. Why?
It's the first stop.
It's the first capillary bed the blood hits after leaving the gut via the portal vein. It just gets stuck in the filter.
That makes sense.
But other times it's about tropism, a specific affinity. Prostate cancer famously loves to go to bone. Lung cancer often goes to the brain and the adrenal glands. There are specific chemical signals, chemokines, that act like a docking signal, attracting the seed to that particular soil.
And some soils are bad for seeds.
Exactly. Some tissues are non-permissive. Skeletal muscle, for example, is very rarely a site for metastasis, even though it has a huge blood supply. The soil is just wrong. Maybe the pH, the metabolic environment, the constant mechanical squeezing, it's hostile to tumor seedlings.
And once they finally land, they have to grow. Colonization.
This is by far the hardest step. A single cancer cell landing in a completely foreign organ is like a person landing on Mars without a spacesuit. It has to survive and engineer a new niche. It has to trick the local stroma into building it a new home and providing a blood supply. Often, these micrometastases will lie dormant for months or even years until they figure out how to thrive.
Which explains why a cancer can recur so many years after a successful treatment.
Yeah.
The seed was just sleeping in the soil.
Exactly. Tumor dormancy is a huge and vexing area of cancer research.
We've talked a lot about the mechanics. Let's pivot slightly to Section 6, etiology. What starts the fire? What causes those initial initiating mutations?
We can group the causes into three main buckets: chemicals, radiation, and microbes.
Okay, chemical carcinogenesis. Robbins distinguishes between direct-acting and indirect-acting.
Direct-acting carcinogens are actually quite weak and pretty rare. Ironically, some chemotherapy drugs themselves, like alkylating agents, fall into this category. They can, paradoxically, cause secondary cancers like leukemia years later.
But the big ones are the indirect ones.
The big ones are indirect-acting, pro-carcinogens. These are compounds that are not carcinogenic on their own. They need to be activated.
Activated by what?
By our own bodies. They require metabolic conversion. And the key player here is the cytochrome P450 enzyme system, mostly in the liver.
This explains the smoker's paradox, doesn't it?
Yeah.
Why some people can smoke their whole lives and not get cancer, and others get it after just a few years.
Precisely. The polycyclic aromatic hydrocarbons in tobacco smoke aren't directly carcinogenic. It's when your liver tries to detoxify them and make them water-soluble that it accidentally turns them into highly reactive molecules that bind to DNA. And we all have genetic variations, polymorphisms, in our P450 enzymes. Some people's enzymes are very efficient at this deadly conversion. Others are not. It's a genetic roll of the dice on how your liver handles the smoke.
That's fascinating. Okay, then there's radiation.
Two main types. UV rays from the sun cause a specific type of damage, forming pyrimidine dimers in your DNA. If your repair mechanisms, like nucleotide excision repair, are overwhelmed or faulty, you get skin cancer.
And the other type?
Ionizing radiation from X-rays or nuclear sources. This causes more severe damage, like chromosome breakage and translocations. This is why it's strongly linked to leukemias and thyroid cancer.
And the third bucket, microbial carcinogenesis, viruses and bacteria. This fascinates me because it just blurs the line between infectious disease and cancer.
It's some of the most fascinating biology. Take HPV human papillomavirus. We know it causes cervical cancer, but how? It has two viral proteins, E6 and E7.
And what do they do?
They are molecular assassins with very specific targets. The E6 protein finds and binds to our P53 protein and targets it for degradation.
It kills the guardian.
It kills the guardian. And the E7 protein finds and binds to our RB protein, inactivating it.
It cuts the brakes.
It's a targeted two-pronged strike on the cell's main tumor suppressor systems. The virus doesn't want to cause cancer. It just wants the cell to keep replicating so the virus can replicate. Cancer is just the long-term collateral damage of the virus trying to reproduce itself.
What about H. pylori? A bacteria.
Yes, the bacteria that's famously involved in stomach ulcers. It causes chronic inflammation, chronic gastritis. And that constant cycle of injury repair over many years dramatically increases the risk of the stomach cells developing mutations that lead to gastric adenocarcinoma, or a specific type of lymphoma called a meltoma. It was the first bacterium to be officially classified as a carcinogen.
Wow. Okay, we're coming into the home stretch now. Section 7, clinical consequences.
Yeah.
How does all of this actually look and feel in the patient?
Well, obviously you have the direct local effects, a mass causing bleeding or obstruction or pain from impinging on a nerve, but there are also these systemic effects that are often deeply misunderstood. The big one is cachexia.
Right. And most people think this is just the patient starving because they lose their appetite or they feel nauseous from treatment.
It is so much more than starvation. In simple starvation, your body is smart. It preserves your lean muscle mass and preferentially burns your fat stores. It tries to save the engine. In cachexia, you lose both muscle and fat, often at a terrifying rate. It is a hypercatabolic state.
The body is eating itself.
It's actively breaking itself down. And it's driven by inflammatory cytokines like TNF, which used to be called cachectin, that are produced by both the immune system's reaction to the tumor and the tumor itself. You can try and force-feed a cachectic patient, and they often won't gain weight. The tumor is literally melting the body down for fuel. It's tragic to watch.
That is horrific. And then there are the paraneoplastic syndromes.
These are the real ghost in the machine symptoms. These are symptom complexes that cannot be explained by the local spread of the tumor or by the hormones that are normally produced by that tissue.
Can you give us an example?
The classic one is a patient who comes in with dangerously high calcium levels in their blood, and they're confused and weak. You do a workup and you find a squamous cell carcinoma in their lung. That lung cancer is producing a protein called PTHrP, which perfectly mimics parathyroid hormone, causing calcium to be leached from the bones. The lung cells have no business making that hormone, but they are.
Or Cushing's syndrome.
Right. A small cell lung cancer that starts producing ACTH, causing the body to flood with cortisol. These syndromes are incredibly important clinically because they might be the very first sign of an occult hidden cancer. The weird symptoms appear long before the mass itself is found.
Finally, we have to distinguish between grading and staging, because patients hear these numbers and they get very confused. I have grade 4 versus I have stage 4.
A huge and critical difference. Grading is histological. It's what the pathologist sees under the microscope. It's an assessment of differentiation. How wild or anaplastic do the cells look? High grade means poorly differentiated, lots of mitosis, very aggressive looking. Low grade means well differentiated.
It's about appearance. And staging.
Staging is anatomic. It's about spread. It asks how far has the cancer gone. We use the TNM system. T for the size of the primary tumor, N for spread to regional lymph nodes, and M for distant metastasis.
So if you had to choose just one for predicting a patient's prognosis, which one tells me more about how long I have to live?
Staging. Hands down, no question. Generally speaking, a small, low-grade tumor that has already metastasized to the liver, that's a stage 4, has a much worse prognosis than a large, ugly, high-grade tumor that is still completely contained in its organ of origin, a stage 1 or 2. Staging tells us the burden of disease in the whole body. It's what dictates the entire treatment plan.
This has been intense, but incredibly illuminating. So, to bring it all home, what does this all mean when we put it together?
If we synthesize all of this, Robbins, Underwood, the molecular biology, we come right back to that central idea we started with. Neoplasia is biology that has been pushed beyond its cooperative limits.
It really is an evolutionary process happening inside of our own body.
Oh, yes. The transition from one normal cooperative cell to a malignant killer involves this whole conspiracy of genetic accidents. The gas pedals get stuck, the brakes are cut, the mechanics are fired, and immortality is granted.
And here's the final thought, the one that really keeps me up at night. Cancer cells aren't foreign invaders. They're not like bacteria or viruses that we can just identify and kill because they look completely different.
No, they are us.
They are the most successful, the most adaptable, the most ruthless versions of our own cells.
That's the profound tragedy and the immense challenge of oncology. We're fighting our own body's mechanisms. The very same tools that allow us to heal a wound or grow from an embryo to an adult, proliferation, ligation, angiogenesis, are the exact same tools that the cancer co-ops and corrupts to destroy us.
It really reframes the whole battle. It's not just about killing a bug. It's about trying to restore order to a system that has rewritten its own rules.
Restoring the rules of cooperation, or more realistically, finding the specific way the rules were broken in that particular cancer and exploiting that unique vulnerability.
Well, on that rather profound note, we were going to wrap up this deep dive.
I really do encourage you to go back to the text now. Go look at the diagrams of the metastatic cascade in Robbins chapter 7. Look at the flowcharts of the P53 and RB pathways in Underwood. Those diagrams are worth 1,000 words.
The podcast is the map. The book is the terrain. Thanks for listening and stay curious.